Uh, so for me, so I'm very honored to host this session instead of Huang Wu. The first presentation will be given by Alicia N. Dr. N's research emphasizes the development of emerging membrane technologies and innovative approaches to solve the pressing water quality and quantity issues. And today her presentation is about transforming intrinsically hydrophilic mexene into superhydrophobic for efficient photothermal membrane desalination. So let's welcome Dr. Alicia N for the keynote speech. Thank you.
Okay, good morning, everyone. Thank you, Dr. Tang, for your kind introduction. So today I'm going to share our recent work on this titanium carbide, the mexene engineered membrane for efficient photothermal membrane distillations. So this work is the collaboration between our groups, Global Energy and Environment, and also the material scientists at the Department of Mechanical Engineering at the CTU. So today my presentation, first I will briefly introduce the membrane distillation and why our research is now the begin with these photothermal materials for solar driven seawater desalinations, and how we turn this intrinsic hydrophilic mexene into hydrophobic for efficient photothermal membrane distillations, and also make some conclusion. Membrane distillation. So increasing water scarcity and the stringent discharge regulations, this necessitate the consideration of unconventional water resource, such as seawater, hypersonic water, and wastewater. And this call for emerging technologies to successfully augment water supply. So as you know, the membrane distillation is thermally driven membrane-based separation process, which is not affected by salt concentration of the feed. That is the reason it can be a promising technology for treating hypersonic water that cannot be treated by pressure-driven reverse osmosis and traditional technologies. And if membrane distillation is combined with waste heat or abundant solar energy, it can be a very attractive process because MD can be operated at low temperature and the pressure while producing high quality water. As you can see this picture here, this is our membrane distillation setup in our lab, and my postdoc, Dr. Jihad, is showing very clean, high quality water which treated by very high saline wastewater. However, we know thermodynamically, the MD require a large amount of energy to evaporate water. And this typical enthalpy of vaporization can be 2 to 3 orders of magnitude larger than Gibbs free energy for seawater separation. So beside of this, the energy and the temperature polarization, which due to the convective and the conductive heat loss also need to be minimized to provide temperature gradient across the membrane to increase the driving force of the water flux. Well, in addition to these energy issues, wetting, scaling, and the fouling is also the challenge that the MD has to overcome to scale up or to expand its applications. And now the question is, in order to reduce this energy consumption, can we use this abundant solar energy? Well, this can be more possible because the recent development in the light to heat, the converting material have opened up the opportunities for efficient exploitation of the photothermal surface heating effect to develop new membrane which can be self-heating and to maintain high temperature gradient. So in general, the photothermal self-heating membrane generate highly effective localized heat so that it can directly utilize at the membrane bead interface by the illumination of light absorption and the light to heat converting material present on top or within the membrane structures. So if we compare with the standard MD process, which we have to use a lot of energy to heat up the bulk of water, photothermal MD using the localized heat. So it can induce the vaporization of the bead stream directly at the membrane surface. So we expect that this will give us higher temperature gradient, which can be used freely to increase the flux. So in order to develop this idea, that the important step is to find out what ideal photothermal membrane for MD that essentially possess highly desirable combination of high photothermal conversion efficiency and the strong wetting resistance, which is still our main challenges. So thanks to the emergence of the various photothermal material, such as semiconductor, carbons, and the plasmonic metals, over the last 5 to 10 years, I think you can find many literatures which demonstrate this new material which can be used under the sun, under the solar light to increase the solar absorption, resulting in better desalination performance. So this covers those are the metals and also the carbon and the GO, and there are many like the natural materials. So it was recently, it was quite published in our literatures. So our study, we start to looking at some new material, which is the also known as a two-dimensional the structure, which is the titanium carbide. You can see that combination of a titanium and also the also nitride, which is called the MXenes. So why? The MXenes was known as broad solar spectrum absorption materials, and also the outstanding photothermal conversions, and also due to this hydrophilic self-stacking properties, it can easily synthesize. And most importantly, the unique localized surface plasma resonance, which has a good potential to be used in the photothermal effect. So as a first step, we tried to synthesize this MXene and then made a pure MXene membrane before we applied to the membrane distillation. And then we make sure our characterization demonstrate the successful the MXene nanosheet the synthesis. So this process is the combination of the etching and also the exfoliations from the raw material, okay, and then followed by the filtration to generate. You can see here, this is a MXene nanosheet. So it has a self-stacking and also the hydrophilic nature, which has a functional group of OH, O, and F. And under the TM image, and we verified the successful fabrication of a MXene nanosheet under the XRD and XPS and through the characterizations. And we have also published this MXene nanosheet for the solar desalination to the applied material interface. So then, after we successful the membrane, the MXene nanosheet, the first step is we applied this mexin nanosheet to solar thermal evaporation process. So in this study, we manipulate this mexin surface to be hydrophobic by the separate assembly of a propylene, because as I explained, the mexin is hydrophilic. So we want to have a hydrophobic nature on top of the mexin nanosheet to make kind of a Janus membrane. And we found that this the propylene and the mexin has a very pi conjugated stacking, which is very stably formed. So it can be tuned as two asymmetric structure of hydrophobic and the hydrophilic layer here. So as you can see, and also under the SEM and the TM image, you can see that this interlayered channel, which was abandoned, which can be utilized as the water channel. So this hydrophobic upper layer is beneficial for the heat localization and the salt resistance, and hydrophilic bottom layer assure the efficient water pumping and the vapor transport. So what we found is this benefiting from those functional group and the propylene, the self-assembly. As a result, this Janus structure obtained a membrane, which has a hydrophobic upper layer and hydrophilic bottom layer, has successfully demonstrated its heat localization and the salt resistance. So under the one sun solar light, we found a temperature increasement. And also this figure explained that the compared to the other membrane, this propylene mexin membrane has demonstrated very high efficiency of the solar conversion. And also the evaporation rate is up to 1.4 kilograms square meter per hour. Well, also due to the nature of these hydrophobic hydrophilic combinations, when we treat saline seawater, it has a very good anti-scaling effect, and the flux was quite stable. So we have compared our study over the literature, because this is our first attempt to make a mexin-based membrane, and we want to see where our result can stand. So based on our literature review, when in terms of evaporation rate and efficiency, our mexin membrane, the result of our mexin membrane can outstanding as compared to the literature when based on our recent study. And in terms of efficiency and the evaporation rate, I think mexin-based membrane has a very high potential to be used in the photothermal desalination. So that was our first attempt to utilize the mexin-based membrane. And then as a second step, we engineer this the mexin membrane to combine with membrane distillation. So again, I'd like to redraw your attention that in the conventional membrane distillation process, we use the external energy to heat up the bulk of water. In the photothermal MD, we use localized heat so that we try to minimize this temperature polarizations. So we have two objectives. One is using the material, we want to enhance the photothermal conversions. And also at the same time, based on our know-how, we want to increase the wettability, because when we apply the membrane to membrane distillation, the first condition is the membrane has to be hydrophobic. Otherwise, it will be very vulnerable for the wetting. But if you remember, the mexin is hydrophilic. And now we have basic two challenges. One is, so how we can turn this hydrophilic mexin to hydrophobic, and also how to overcome this chemical and mechanical stability, which can give us good integration with the membrane support layer. So This is the also combination of our previous study, which we have published in the number of journal using PDMS, combination of the PVDF using the electrospray electrospinning method. So what we did here is, because we already have successfully synthesized the Maxine the solution. So earlier study, because we want to fabricate the Maxine nanosheet, and then when we use the solar desalination, the membrane mechanical strength is still not very critical. But in the membrane distillation, because we want to have sufficient membrane mechanical strength as well as wettability. So what we did is, using this Maxine powder, we mix with the PDMS and the electrospray onto commercial PVDF membrane to see first whether we can make a stable integration of this Maxine layer on top of the PVDF membrane. As you can see from this image, so this is a commercial PVDF, the cross-section image, and we have decorated a very thin Maxine engineering layer, which is super hydrophobic. And that this hydrophilic Maxine was captured by PDMS, and then they have successfully integrated on top of a PVDF membrane. So now you are looking at the same image of PVDF, and the surface, the image of PDMS, Maxine, PVDF membrane here. So now let's look at the membrane properties. When we use the different the Maxine concentration, so like this 40, 60, the 50, you can see here that membrane display much stronger and broader solar absorption. Okay, of course, compared to the PVDF membrane, because PVDF membrane is not for the thermal membrane, our Maxine membrane shows a very broad solar absorption and also the high peak. And how about the temperature? Okay, within 3 minutes, we found that this PDMS Maxine membrane, the surface temperature can be increased as high as 85 degrees. Okay, that is under 1 solar. And you are looking at the IR thermal image of this Maxine membrane compared to the PVDF membrane. Then you may wonder, how about the thermal conductivity? Because this is a photothermal process. And if it is used as the membrane distillation process, if there is a very high thermal conductivity, I think it will be also vulnerable for the temperature polarization. Well, because of our unique structure of the Maxine embedded in the PDMS, which can also create a lot of air capsule inside. Well, surprisingly, our data shows thermal conductivity is even lower than commercial PVDF membrane. So we make sure that it will not compromise this photothermal effect to be engineered in the membrane distillation process. And this is a schematic diagram that when we architecture this tuning the hydrophilic to hydrophobic, the Maxine, which captured in the PDMS, even is as a kind of a nanosphere size, it will create the air pocket, and also it can reduce this thermal resistance. Well, how about the wetting? But this is not surprising because we have quite many years of our experience to tuning the surface of the membrane. However, it was quite surprised to me that when we use the Maxine PVDF, the PDMS, the electrospray, which created this kind of a nano-size of sphere, well, the contact angle of this the membrane is increased to up to 172, which is a super hydrophobic. And even it has a water bouncing effect. So when we monitor under the high-speed camera, actually it has a very low surface energy, which can bounce off the water droplet. We have done quite intensive characterization to see the wetting effect using our homemade system, which can monitor the impedance and try to understand what is the wetting mechanism. But due to time limited, I think I will just show the graph, and just want to say that our membrane was very good, has a good anti-wettability. And now we are, this paper is under review in the Nature Communications, and hopefully you can read our final article in due course. Well, I think this is our last slide. So I want to conclude that under the no sunlight, the Maxine membrane and the commercial PVD membrane has no difference in terms of a flux. However, when we utilized solar energy under the one sun, the Maxine membrane, the flux was increased significantly. It's up to 2.88 kilogram meter square per hour. And of course, when we increase the solar density, while the PVDF membrane has almost no differences, the Maxine membrane shows the increasement of the flux. And more importantly, when we apply our membrane to treat this hypersaline brine, which has about 10% of salinity, the NaCl solution, well, our membrane demonstrates a very stable condition compared to the commercial membrane. Then what about the solar efficiency? So we have to calculate the apparent solar to vapor conversion efficiency. And then we did also intensively review to rule out what is our solar efficiency compared to the other literature. Of course, compared to the commercial PVD membrane, which has less than 20%, our data shows 89%, which is quite comparable, and I can say that this data is quite outstanding. So when we apply this photothermal membrane distillation process, you can see that we use the direct contact membrane distillation module with a quartz window area about 36 square centimeter. And then we try to verify it under the different solar density, what will be the flux generation. And then you can see that under the IR image, what is the temperature increase here. So to conclude, we have developed the Maxine engineered membrane that impart efficient localized photothermal effect and the water repellency for sustainable photothermal membrane distillations. The efficient solar harvesting capacity of Maxine enables photothermally localized, the surface, the heating of the membrane to circumstance the inherent heat. The feed side induce the continuous water to vapor transitions. And this high electrically conductive Maxine plays a structure directing role for the self-assembly of a uniform hierarchical polymeric nanosphere on each surface via electrostatic spraying, transforming the intrinsic hydrophilicity into hydrophobicity. So benefiting from this interfacial engineering, this PDMS, Maxine PVD membrane, is endowed with a constant high cross membrane, temperature gradient, as well as a strong wetting resistance. And we have demonstrated this the water production rate up to 2.88 kilogram square meter per hour, and good stability when treating hyposaline under one sun irradiation. Well, this work presents the facile strategy on developing well-fulfilled Maxine membrane for potential seawater distillation from the material perspective. However, still the emerging vaccine material membrane are still limited to lab scale research, and there is still a long way before achieving large scale application in the future. So with this, I'd like to conclude my talk, and thank you very much for your attention. And also, this is the work from the collaborators and also our members. And also, I'd like to have your the question from the floor.
Thank you. Thanks, Dr. Ann's presentation. So you have 2 questions. Can you see them?
Yes.
Okay.
Okay, so there is a question that what is the pipeline stacking? Yeah, so when we make a genus membrane, then you need to have a interaction of a material to make a stacking, right? So when you use a polypropylene and the vaccine, the mechanism of their interaction is pipeline stacking. And the second question is, when you fabricate the membrane for MD, what is the purpose of the mixing PDMS? Okay. Yes, we have actually published quite a number of papers to make this PDMS sphere to create re-entrance structure. But when we use the PDMS alone, this sphere structure is a microstructure. But interestingly, when we combine with the vaccine, so the vaccine, this hydrophilic layer will be captured by this hydrophobic PDMS layer. So the vaccine inside will induce photothermal, and the PDMS layer will prevent wetting from the water. So it's like a combined 2 effects into the 1 single layer to have a double effect of the membrane distillation. Yes, so how did you control this coating to be nano size? Yeah, well, this is we have to do a lot of optimization. And if you're interested in the detailed procedure, I think our paper will be published very soon. And also, yes, we can have some discussion when directly. Okay, and then the other question is how to realize a stable combination of PDF film and the vaccine, and whether the vaccine photothermal layer falls off. Yes, right. Well, this is the, so as I mentioned, the first thing is that we were struggling so I think everyone knows that when we use a nanomaterial, the first thing is how we can have the stable, interaction, right, between this particle and the polymeric, the substrate. So we first use our know-how to do the electrospraying. Well, I can say that still I cannot say this is 100% super stable. So we are now working on some optimization. This is also a good method to start with. However, yes, I think in the long term, maybe there is a leaching. So we are now thinking about how about the other, looking for some of the other option to improve this, the stability of this layer.
Thank you. Thank Dr. Ann's answer. And I noticed that there are also other questions raised in the chat part, but you can answer them by typing maybe or later, because we don't have much time. Yep, we have to, I'm sorry. We have to
move on to, yes,
we have to move to next presentation. The next presentation comes from Dr. Liu Yongjie Liu. Right now he is a PhD student and currently works in Center for Membrane Advanced Water Technology, Halifa University. Yongjie did research in membrane technology, desalination, and membrane distillation. So let's welcome Yongjie to give his presentation about experimental, direct contact membrane distillation with negative feed pressure for enhanced scaling resistance and vapor flux. Thank you. Let's welcome Yongjie Liu.
Okay, thank you. Hello, everyone. I'm Yongjie Liu. Today, I was very glad to introduce our new membrane distillation configuration, negative feed pressure direct contact membrane distillation for enhanced scaling resistance and the vapor flux. Okay, first, I would like to introduce the current status of seawater desalination and brine production. Now, rising water demands and the diminishing water supplies are exacerbating water scarcity in most world regions. Now, desalinated water is expected to play a key role in narrowing the water demand supply gap. You can see it explosive growth in the past 30 years. With the rapid expansion of desalination plants, the current global desalination capacity could reach about 100 million square meters per day. However, global brine production is 141.5 milli square meters per day, which is about 50% greater than the previous estimates. Most of them are directly discharged back into the sea, which changes the ecological environment of the ocean and may kill the marine life near the desalination plants. Hence, now brine production and energy consumption are key barriers to desalination expansion. And innovation and developments in brine management and the disposal options are required. Membrane distillation is one of the most potential technology to treat brine. It is a thermally driven desalination process where a macroporous hydrophobic membrane acts as a physical barrier of direct liquid transfer between the hot feed and the cold distillate streams. Due to the transmembrane temperature gradient induced the vapor pressure gradient, water vapor transports through the membrane pores from feed to distillate. As vapor pressure is weakly dependent on feed salinity, MD is an attractive process for hypersaline brine treatment, where the osmotic pressure requirements makes reverse osmosis inapplicable. And there is no applied pressure, which reduced the electrical energy of the low-grade energy like solar or geothermal heat is used in MD applications. Due to the principle of the MD, 100% theoretical rejection of non-volatile components is achieved. However, MD has now has four main challenges. First is the temperature polarization, as mentioned with Dr. Alicia in the previous presentation, and the scaling and falling will generate a cover of the inorganic scalants or organic foulant on the membrane surface, which will block the force to reduce the membrane distillation performance. In even more serious case, scaling and falling will cause the wetting. When wetting occurs, a bridge will form between the feed and the distillate, and the distillate water will be polluted by the wastewater at the feed. The latest theory to solve this problem is the slippery surface. On slippery surface, very limited interaction of the liquid and the membrane polymer could not allow the formation of nuclei on membrane surface. Even if the solution contains crystals, it is also very difficult to attach to the surface. Here is a lot of works on making a slippery surface with membrane modification to change the non-slip boundary to a slip boundary. But most of them is complex and high cost. So, is there an easy way to achieve the slippery surface without membrane modification? Here is our answer. In regular DCMD, pump is put before the inlet of the feed channel. So the water is be pushed by the pump, and the positive pressure is achieved in the feed channel. So you can see the liquid gas interface is concave into the pores. So if we can give a force to the liquid gas interface, pull out, and to the membrane surface, our solution is move the bump from the inlet to the outlet. So the work is sucked by the bump, and the negative pressure will be generated in the feed channel. In our work, we give above before the inlet of the feed channel to control the value of negative pressure. Here is the schematics and the photos for our membrane test device. Let's see the performance of the MPDCMD. First, I will introduce the scaling resistance. In our experiment, we use a commercial PVDF membrane, what is a very hydrophobic, a little hydrophobic membrane. And the feed is the 2000 ppm calcium sulfate solution, which saturation index is 0.09. You can see when we use the hydrophobic CPVDF membrane, it has a very similar scaling resistance performance with the hydrophobic surface in an optimal condition named the post-flow in our previous work. And there is the photo and the imager of SEM images. You can see a lot of crystals is covered on covers on the membrane surface at the positive feed pressure. However, when we use MPDCMD, in the area free from spacer, there is only a little crystals. But because we use a spacer to spot the membrane, the spacer itself is not could not resist the scaling. So the scalant is growing on the space first and move to the membrane. Here is our evidence. So this is an evidence that we successfully generated a slippery surface with a commercial PVDF membrane without any chemical or physical modification. And the second very interesting point is the flex enhancement. You can see when we use MPDCMD, it is about 160% with the original one. Then we trying to expand it. We know that there were two main resistance in the water of vapor transfer in MD. They are the Newton diffusion resistance and the molecular diffusion resistance. Because we changed the pressure in the feed channel, so the pores in the air pressure in the pores is also changed. So the J is related to the two resistance of the vapor transfer and the driving force. We calculate the two both diffusion resistance. We can see that with the different temperature and different pressure, Newton diffusion resistance is almost the same. But with the decrease of the pressure, the molecular diffusion resistance is declines linearly at different temperature. So we used this data to the depth gas model to calculate the flux. But you can see our model data could not fit the experimental results very well. So it means that it is not really only the resistance contributes to the flux enhancement. HB has the driving force is also changed. Let's see this picture again. When we achieve a slippery surface on membrane, the slippery boundary, it will reduce the temperature polarization, right? And when we change the convex liquid gas interface in the pores to the concave liquid gas interface on the membrane surface, it will reduce the heat conduction across the membrane. So we give two factors to these formulas. We give phi1 to the effect of the slip boundary, and phi2 to the less liquid solid interface effect. Now we can find, wow, it is a very good fit, right? And then we catch the data of the membrane surface at the feed and distillate. You can see with the temperature, with negative feed pressure, the temperature at the feed surface, it is increased. It's increased. But because the flux is also enhanced, so the distillate temperature is also increased. So how is the driving force? Because the temperature of the at the feed and at the feed membrane surface and distillate membrane surface is changed. So how is the driving force? The driving force changed. Here is the data. As you can see, when we achieve only a little negative pressure, the driving force is increased very large. But with we reduce the pressure more, the driving force is declined. So here is the two contributions in our flux enhancement. First is driving force, and second is molecular diffusion. We can conclude that when we add a little negative pressure, optimal heat transfer was main contribution. But with the pressure decline, the reduced molecular diffusion transfer would be a more contribution instead of the optimal heat transfer. Here is the thermal efficiency. You will see that when we use the negative feed pressure DCMD, we can catch a very high thermal efficiency. This is the result of the less heat less heat transfers through the membrane, and more heat is contributed to the water evaporation. Okay, so this is NPDCMD is a very simple technology to make a slippery surface without chemical and the physical membrane modification and the additional input energy. NPDCMD has the good performance of scaling resistance as a super hydrophobic membrane, which has a slippery surface. Compared with the regular MD, flux was enhanced about 160% with the NPDCMD. There is two main reasons of the flux enhancement in our study. The first is to reduce the molecular diffusion resistance by negative pressure of the air in the pores. Second is optimal heat transfer by slippery boundary and the decline in solid liquid interface. And the last one is the conclusion is as the negative pressure decreases, reduced molecular diffusion gradually replaces optimal heat transfer as the main contribution of flux enhancement. At last, I would like to thank Dr. Shi Hong, Dr. Tao, Thomas, Dr. Zhang Xin Wang, Dr. Hassan Rafat, Dr. Hua-Bing Ying to support this work. And I also want to thank this fund to support this project. Okay, thank you for your attention. Any questions or suggestions? Hello.
Is anyone have concentration have questions? So if no, I would like to know that. So is this a collaboration between Professor Tao He and your university?
Yeah.
I mean, yeah. Okay. So have you published this? So
No,
I
it's
think
under
this is
review.
a very interesting.
Yes, it's under review. It's under review.
On the review. Okay.
Yes.
So we will see them because for the modeling, I think if there's more details about the modeling work, we can understand better. Yeah. So, okay, we have a question.
Thank you.
Can you see the question?
Let me check. Okay.
Can it also be applied to membrane folding?
Okay. Organic folding, we didn't do the things, but I think it could be, because when we use the negative feed pressure, we could achieve the liquid gas interface. But what is very unfortunate is that until now we cannot observe our assumption. So I think if we can build a device to observe the liquid gas interface on the membrane surface, it will be a very solid evidence to our assumption.
Hi, Liumjie, I have one simple question.
Okay.
So have you done overall the system analysis that because you are lowering the pressure at the permeate side, and then you also increase the performance, and then overall this specific energy consumption is has a gain value?
Sorry.
So when you reduce the pressure, right?
Yes.
And then definitely you need to have some energy input. So
okay.
Yeah. So overall, your energy consumption is what do you think is any value on your? Can you reduce the overall energy consumption by having this negative pressure to increase your performance?
Okay, that's a very critical comment. Because when we in the regular DCMD, we should have the pump to push the water, right? But how we achieve the negative pressure, we only change the position of the pump. So
you mean that there is no extra energy required?
Yeah, in fact, it should be, because when we close the valve or anything, we need to increase the bump rate.
Okay.
So there is, but I think in membrane distillation, the bump energy is a very little contribution in the whole system, right?
Okay. All right. Yeah. So thank you very much. So yes,
okay,
thank you, Dr. Tang, for sharing the
Yeah,
session
thank
together.
you.
And then let's move on to the next speaker.
Okay, I will go. Thank you.
All right. Yeah. So our next speaker is the Miss Zhao Haoyue on behalf of Huan Wu from Beijing Jiaotong University. So she's going to share her talk on experimental and the theoretical research of polarization phenomena in the vacuum membrane distillation for ionic liquid separations. Please unmute yourself. Ms. Zhao, can you unmute? Yeah, okay.
Thank you. Can everyone see my screen well?
Yes.
Okay, thank you. Hello, everyone. I'm Haoyue Zhao, a master student from Beijing Jiao Tong University. It's a great honor for me to listen so many wonderful lectures here. As my tutor Huan Wu has teaching task and not attending the meeting, I will give the report on her behalf for the time being. So today my topic is about experimental and theoretical research of polarization phenomenon in vacuum membrane distillation for ionic liquid separation. And next, I will introduce this work from the 4 parts. Firstly, as we know, ionic liquids are organic liquids composed of organic cation and inorganic or organic anion. IL are characterized by non-volatilization, conductivity, viscosity, and designability. So they have been widely used in electrochemistry, separation process, biomass conversion, and other fields. Although IL are considered as green solvents, they have a biological toxicity and can cause serious pollution if released into the surrounding environment. For example, the dissolution and regeneration process of cellulose usually produce abundant 1 to 5% IL aqueous solution. So in recent years, the recovery methods of IL mainly include distillation, extraction, adsorption, and memory separation technology. And among them, memory distillation is more favorable for recovery IL solution because it has 100% theoretical rejection of non-volatile compounds with a high flux and rejection rate. As we can see, there are 4 different modes of MD, including DCMD, AGMD, SGMD, and VMD. Among them, VMD is deemed to have higher commit flux and less conductive heat loss than the other configurations. So we choose VMD as a method of recovering IL solution. And in our previous study, the VMD experimental system composed of self-made membrane components was used to separate and concentrate IL aqueous solution. The results shows that the concentration polarization lead to the degradation of membrane performance, and membrane falling was observed obviously in the 3 concentration stages. Therefore, the mass and heat transfer and polarization phenomenon in VMD process are worth studying. As shown in the left picture, the heat and mass transfer process mainly include 4 steps as below. In addition, a series of experiments had showed that the effect of temperature polarization on heat and mass transfer was greater than that of concentration polarization in conventional salt system. And so what will happen in VMD for IL solution separations? In order to find the answer, in this work, we used a PTFE membrane to separate and concentrate 3 different IL solutions in VMD experimental system. The structure parameters of PTFE membrane and the physical properties of IL solutions were obtained by experiments. We used MATLAB languages for interactive method to calculate the final temperature and concentration of membrane surface. The original temperature and concentration of membrane surface were calculated by using the corresponding empirical formula of heat and mass transfer. And the specific calculation process is shown in the left picture. So let's see the results. Firstly, the effect of feed flow rate on the performance of VMD in beam chloride aqueous solution were investigated. As can be seen from picture A, the rotation rate of PTFE membrane was stable above 99.9%, indicating that PTFE membrane had good rejection. Besides, if only TPC was considered, the simulated flux was higher than the experimental value. But if TPC and CPC were taken into account, the simulated flux was in good agreement with the measured values. Secondly, with the increase of flow rate, the mass transfer and heat transfer coefficient of the process increased, and the transmembrane pressure difference of the system was raised. Meanwhile, as shown in picture D, both TPC and CPC were reduced, and the degrees of CPC was greater than that of TPC. Feed temperature was one of the key factors affecting VMD process. As shown in picture A, with the feed temperature increase, the flux also increased, which was only caused by the increase of water saturated vapor pressure and the increase of transmembrane pressure difference. Similarly, only when both CPC and TPC were considered, the simulated flux was highly consistent with the experimental value. The heat transfer coefficient and mass transfer coefficient increased, and picture D showed that both TPC and CPC were intensified, and CPC increased more than TPC. And in picture A, we can see that as the feed concentration increased, the flux decreased gradually because the decrease of the water activity coefficient and the transmembrane pressure difference. The simulated flux was in good agreement with the experimental value when CPC and TPC were both considered. Moreover, the increase of TPC was caused by the increase of IL solution concentration on the membrane surface. The intensification of CPC result from the decrease of mass transfer coefficient. So the range of CPC was greater than that of TPC, and concentration polarization was the main cause of flux decline. How about the flux in other IL solution? Therefore, we selected Hme chloride and Bmine hydrofluorobatory aqueous solution for experiment. The fluxes of the two IL solutions at different flow rates were compared. It was found that the membrane flux of the two solutions increased with the increase of feed flow rate. However, if only TPC is considered, the simulated flux of Hme chloride differs greatly from the experimental flux at a low flow rate. But simulated flux of beam tetrafluorobate has high coincidence with the experimental flux, which indicating that in this process, the influence of CPC and flux in Hme chloride system is greater than that of in beam system. And with the increase of feed flow rate, TPC increased, but CPC decreased both in the two IL solutions, which was beneficial to elevation of a polarization phenomenon. So the order of CPC at different flow rates was as followed. Accordingly, we compared the simulated flux and experimental flux of the two IL solution at different feed temperature. And we found that their variation was consistent with the beam chloride aqueous solutions. This is because the actual flux increased with the increase of feed temperature, and the simulated fluxes were in good agreement with the experimental fluxes. Similarly, the CPC of HME chloride has a greater influence on the flux than that of beam tetrafluoroborate system because the viscosity of the HME chloride is higher. As the feed temperature increased, TPC decreased while CPC increased, indicating that the polarization phenomenon intensified eventually, which eventually caused the experimental flux to be less than the theoretical flux. Moreover, the diffusion coefficient of beam tetrafluoroborate is higher than that of HME chloride, making the CPC of HME chloride greater than that of beam tetrafluoroborate. So the order of the CPC at different temperatures was as follows. And the experimental flux of the two IL solutions decreased with the increase of the feed concentration. As before, the simulated flux was in good agreement with the experimental value when both TPC and CPC were considered. Interestingly, for beaming tetrafluoroborate, when only TPC was considered, the simulated value of flux increased with the feed concentration increase, while the experimental value decreased. With the increase of feed concentration, TPC and CPC increased. So to sum up, we come to this conclusion. In IL solution with high concentration and high viscosity, the influence of CPC is greater than that of TPC in Vmd process. Next, the CPC and TPC of the three ionic liquids system under various conditions were compared. The following results were obtained. This is the order for CPC under the same feed liquid flow rate and temperature. The order was as followed. And then these features showed the relationship between feed concentration on membrane surface. As we can see from right pictures, the CPC of beam tetrafluoroborate was largest at different feed concentration, and the order of IL concentration on membrane surface at different concentration was as followed. Above all, we come to the conclusion. First, the relevant models were established to calculate parameters in IL aqueous solution, and flux prediction models were established based on heat and mass transfer fitting empirical formula. The predict flux were in good agreement with the measured value when both CPC and the TPC are considered. And the second one is the effects of different operation conditions on TPC and CPC were calculated by flux prediction model, and the result indicating that the increase of feed temperature and concentration aggravated CPC in Vmd process. And the second one is the influence of CPC was greater than that of TPC in Vmd for IL solution separation on account of IL was a high concentration and high viscosity system. That's all. Thanks for your attention.
All right, thank you, Xiao, for your interesting talk on the modeling with in respect to the concentration polarization and the temperature polarization. So any question from the blower? Because due to time limit and we are a little bit behind of schedule, so I think we're gonna move on to the next and also the last speaker's talk. So thank you, Xiao, and the leader Mong is here.
Yes.
Yes. Okay. So our next speaker is the PhD students at the Zhejiang University. And he is going to share a study of a membrane wetting mechanism in sodium chloride solution desalination process by membrane distillations. So Zhao, can you stop sharing the screen and the leader can share the screen?
Okay,
Oh, all right. Wait a minute.
Okay, leader. Yes, can you share your screen?
Yeah. Yeah. Can you still can you see my screen now?
Yes. Yes.
All right. So thank you for the introduction. And first, I'd like to thank the organizers of this conference that they invite me to present this talk. And today, as the topic says, I would like to focus on the wetting mechanism. And my talk is divided into 4 parts. I'll start with a brief introduction about wetting mechanism research. Then we will look at the experimental design and results. And finally, I'll try to analyze the wetting mechanism from a microscopic view. As you're all aware, membrane distillation is a thermally induced separation process driven by the vapor pressure difference between the 2 sides of porous membrane. Compared with other membrane separation technologies such as reverse osmosis and nanofiltration, it has a higher theoretical rejection of non-volatile substances, which means it's suitable for the treatment for high concentration solutions. For example, it could remove organic and heavy metals and concentrate sugar solutions like during beverage production. However, the process stability of membrane distillation is still a challenge in the industry due to membrane wetting, like this figure shows. When membrane wetting occurs, the feed may pass through the membrane directly into the permeate side during the membrane distillation. The wetted membrane is like this. And therefore, it's critical to understand the membrane wetting mechanism and find out wetting tolerance methods for large-scale application. Indeed, during the last decades, a various wetting mechanism was proposed. For example, according to Professor Shi Hongling's research, the membrane wetting may be caused by the absorption and accumulation of surfactants. And the research of Professor Emily Lack's team suggests that the wetting behavior depends on the matching relationship of surface energy between the solute and the membrane. Also, the membrane wetting caused by organic and inorganic fouling were reported, of course, and changes in operating conditions were also able to cause membrane wetting. Like yesterday, Ju Yongli from Korea reported the inhibition of fouling by patent sound vibration. And among all the above situations, it's generally accepted that the inorganic scaling is one of the main factors leading to membrane wetting, especially when treating inland or municipal water. But the wetting mechanism in pore level is still unclear. Many methods have been applied to detect the wetting process for understanding the membrane wetting behavior. For example, Florian Kiefer and others from Germany use in-situ optical measurement to detect the scaling process. And by using AC impedance methods, Professor Shi Hongling's group realized the early detection of membrane wetting and the detection of dissolved tracer incursion named DTTI mentioned a method invented by Professor Kapser's team visualized the wetting progress. However, because of the size and structure limitations of the membrane pores, it was difficult to find direct evidence inside the membrane pore at the microscopic scale, making it still a challenge to establish the connection between membrane wetting and microscopic changes. This leads to my next point, which is how could we directly evaluate the wetting process in micro level or pore level? To further understand the pore level behavior of membrane wetting, we use the electrous-bound nanofiber membrane to analyze the wetting process of vacuum membrane distillation. Compared with the conventional dense membrane, ENM has the distinct open pores. It's constructed by weaved nanofibers so that it has a wide range of pore size distribution. Meanwhile, the open pores were helpful to overcome the realizing limits. And based on our previous work, we've modified the surface of ENM to improve its hydrophobicity and give it more significant resistance to wetting. And here is the configuration of the lab-scale vacuum membrane distillation device. This system consists of two parts, and more information about this system could be found in our previous paper. All right, this is the Vmd performance. In the first 10 hours, the permeate conductivity kept constant, almost, and the flux gradually dropped around 10%. And then the permeate conductivity dramatically rose, while the flux showed a slightly increased after running for around 11 hours, which indicates that occurrence of a severe membrane wetting phenomenon. And after this, we regenerate the wetted membrane. The regeneration process was performed instantly in the device. Just replace the feed by deionized water and increase the pressure to pass through the membrane in liquid form. After regeneration, as you can see, the flux and the permeate conductivity return to the initial value. That is to say, the membrane wetting disappeared. The SEM results show the change of cross-section morphology during the Vmd process. Initially, the membrane was clear, and after 6 hours, a small number of crystals appear on the surface of the membrane. And about 12 hours later, crystals could be observed at the pores of the permeate side. And after regeneration, it shows that the deposited crystals dissolved. The EDS spectrum verified that the crystals were sodium chloride, of course. And besides, the variation of the relative intensity of sodium and chloride element also indicates that the distribution density of sodium chloride in the cross-section is increasing, which means the membrane wetting was due to the gradual precipitation, and the crystallization of sodium chloride is from the surface pores to the interior of the membrane. And to further analyze the effect of the precipitated sodium chloride on membrane surface and properties, we use mercury incursion method to characterize the variation of membrane pore volume and porosity. Compared with the virgin membrane, the porosity of the wetted membrane was reduced around 10%. Yeah, it's consistent with the flux drop. And after regeneration, the porosity and flux was restored to the initial values. Therefore, it's a decrease in porosity caused by the sodium chloride crystallization that leads to the flux decline. And interestingly, the pore volume on smaller pores decreased significantly, while the larger pores changed slightly. It's indicated that the small pores were more susceptible to be filled by sodium chloride. Now that the variations at the pore level has been explored, it's easy to understand that macroscopic behaviors, such as water contact angle, WCA, and liquid entry pressure, LEP. As the figure shows, the WCA and LEP shows consistent changes, which means the sodium chloride crystallization was the primary factor affecting both WCA and LEP. It alters with intrinsic hydrophobicity of the membrane. Moreover, according to the Laplace Cantor equation and the LEP results, this transform occurred not only on the membrane surface but also inside the pores, which was consistent with the FCM results. Now, I would like to draw your attention to this point, the wetting mechanism. Firstly, at the micro scale, many studies have mentioned the water bridges caused wetting. Indeed, the evidence from this study indicates that the sodium chloride crystals do not fill the entire membrane pores when membrane wetting occurs, but partially precipitating the smaller pores. This provides evidence that the water bridge must be present when wetting occurs. And secondly, the whole wetting process could be divided into 4 stages. And we believe that the stage 2 and 3 should be regarded as the K stages. Actually, we suppose a crystalline wetting closed loop process dominates the wetting transition between the 2 stages. What I mean to say is, because of the concentration polarization, once the feed gets surface saturation, sodium chloride particles will precipitate and fill in the membrane pores, resulting in a decline of porosity and membrane flux and turning the interface between NM fiber and feed from hydrophobic to hydrophilic. Then this converted interfaces expand the range of local wetting, like this, which creates a pathway for the feed incursion. And driven by pressure, the feed will go deeper into the membrane. And the evaporation interface, that is the frontier, will move towards to the permeate side. The rounding of the frontier activates the concentration polarization, which leads to more crystallization of sodium chloride. This process, the crystallization and wetting reinforce each other. It will accelerate the membrane wetting process and make a separation performance drop rapidly, which means unless cut off this cycle, the membrane wetting is inevitable. An easy way to think of is to flush before wetting occurs. So we designed a periodic flushing process to break this vicious circle and achieve a stable desalination process. So here is a quick recap of the main points of this presentation. Firstly, we fabricate EMS to overcome the limitations of dense membranes. And secondly, some pore level changes were tracked during a wetting process, which solved the wetting mechanism. And last but not least, we proposed loop processing membrane wetting, which should be, we suppose, the primary consideration when designing the anti-wetting strategies. And finally, I would like to thank my supervisor and my collaborator and the founder. So that brings me to the end of my presentation. Thank you for listening, and I'm happy to answer any question.
Right, thank you, Demong, for your adding the new knowledge of a wetting mechanism into the membrane distillation group. So can we have a question from the floor? Okay, so I have one question. So, so what you suggesting for the to alleviate this the scaling is the last slide you mentioned about the flushing.
Yeah. So I'll open my slides.
Yeah.
Minutes.
So we understand based on your presentation that the scaling is actually induce the wetting.
Yeah, because we suppose that for sodium chloride, when distillation, yeah, this slide, right? is the sodium chloride that changes the the interface between the ENMS from hydrophilic to hydrophilic. So this this contact angle changes leading to the decrease the LEP so that the feed water could penetrate into the membrane. And because it is sodium chloride, it can be dissolved. So we use hot water to dissolve the sodium chloride so that this this process could be could achieve a continuous MD process. But for some other scale like calcium sulfate is more common, and this method perhaps couldn't work perhaps, and maybe by if you want to cut off the circle, perhaps to flush the membrane by some chemical regions, and that is how to avoid wetting by by cutting this loop. And perhaps in the future we could design some strategies like in the chemical industry to flush or what else, just to cut off this circle so that the crystallization could be inhibited, and then the wetting could be avoided, I guess.
But I'm still wondering, how can you define this critical the crystallization point?
Oh yeah, this is this is
because
more time,
now only
right?
you are looking at the conductivity from the permeate side and the flux data, but there will be some delay of this crystallization.
Yes. Okay. Actually, this is according to the first slides, the performance, and we could know that around about 10 or 11 hours here, the membrane is about to be totally wetted. So, and before that, we'll regenerate the membrane.
So that is, I think, in line with our from the audience, Crystal Long asked whether it can control the partial wetting at crystallization process, because when now we're only looking at the when after the flux is declined and the conductivity is still okay, but when the flux is declined. So whether how can we see this the progression of the crystallization which induce the kind of partial wetting?
Well, I guess we should to do more research about different types of feed water. Yeah.
All right, because, and then there is an interesting also question from the Dr. Bei Guo. So his question is, if crystallization happens in the pore and the membrane is fully dry, do you think it is possible to remove the salt crystal by just fresh water cleaning? If wetting is by the crystal, and because crystal is solid structure, and then so he said that it's dry and
Yeah, actually we proved it. Like this, the EDS results after regeneration, the the sodium and chloride element peak dissolved, disappeared, like the blue lines shows. Yeah, and from the SEM results, it shows the sodium chloride disappeared too.
Right. So I think in the plenary talk, Professor Kim Sing-hyun said that the wetting is kind of irreversible, but what you are suggesting is that we can control wetting as by the membrane regenerations.
Yeah, but actually we would like to use this ENM because it has open pore structure. Perhaps the ENM could be used widely, like to understand the different falling or wetting types of feed water, and more than sodium chloride. And this is just as a prototype. And we choose sodium chloride because it's more common and is difficult to remove.
All right, so thank you very much for your presentation, and also thanks to audience to
Thank
stay
you.
till late. Yeah. Okay, Lee, you have a question?
Yes, yes.
Yeah.
I have a question for your mechanism. Yes.
Yeah.
I
Okay.
don't, I can't believe the water wetting the small pores first.
Yeah, it's interesting, and actually this is I suppose this question is a good question, and just based on our for current evidence, of course it's not persuasive that the the crystals is prefer to crystallize in the small pores. But the evidence is that.
Yes, I think the evidence does not prove it is wetted the smallest pore first, because like when you have
when the crystal,
because all the your pores is connected, right? They are connecting. So when the water comes to the big pore first, but it will be when it is wetted, it will wet it at the
surrounding area first.
It will,
it's the surrounding area, like this
on the
picture
polymer
shows.
first, right?
Yeah.
So the polymer, if there is a big hole here, okay, and here is a small hole, like there something big hole here, so it will be crystal first when you wash or anything, when you put the when you catch the membrane out, you will see all pores, it will be crystals, right? So I think that it should be, because you have the LEP formula. The LEP formula told you that it will be wetted by the biggest pore first, right? So
no,
the results for your pore size, it's only could not prove your mechanism. I think it is only says that there is more crystals generated between the fibers.
No, actually, there is conditions perhaps you may neglect it because this is hydrophobic membrane, and all of the pores. The condition is all of the pores is little enough to defend the feed. So normally, and those feed can't invasive into the pores. So the pore size, I mean, the Rmax is sufficient to defend the feed to incursion. The conditions you mentioned is I've noticed. I can still recall that it should be the paper written by Shi Honglin. They made a research about silica, and the silica deformed the membrane pores, so the Rmax is expanded and the LP is larger than before. And at this condition, though yes, you're right, this result is not sufficient to prove that, or it could be a solid proof that the porosity variation. But based on our normal understanding, and the condition and the formal condition is the ENMS, the pore size of ENMS is little enough to avoid the feed to invasive into the membrane. So I guess it's a reasonable conclusion.
All right, so I think this is a very interesting discussion. So I think Wang, you can also revisit your hypothesis to verify based on more your the future studies, and hope to read your paper, because I see that some of your work is now under review. So hope to read your paper soon. Yeah. Okay, with this, thank you for the speaker and also audience to stay till the end of our schedule, and hope you enjoy the rest of the conference and hope to see you in person in next conference. All right, thank you very much. Bye-bye.
Thank you.
Bye.